This is Unit 11, Lesson 7. In this lesson, we'll talk about the ideal gas law, which is a gas law that deals with gases. And remember, gases are ideal in the sense of they are perfect. They behave perfectly, and which is true for most gases, as long as you're under moderate conditions. Now, the ideal gas law will bring together all the four gas laws we've studied: Avogadro's law, which dealt with moles and volume; Charles, temperature volume; Gay-Lussac's pressure temperature; and Boyle's pressure volume. If you remember, the first three here were direct, meaning if one variable increases, the other also increases. And in order to represent mathematically a direct relationship, you would divide the two variables to give you a constant. The last one was an inverse. You have to multiply the two variables to give you a constant. So first of all, what we're going to do, we're going to take all these constants and put them together, and instead of calling them k, little k, we'll call it big R. This big R will appear in the big gas law that we're about to show you. And here is how it appears in the big gas law. This is the ideal gas law. It is PV equals nRT. Pressure times volume equals moles times R, the big constant, times temperature. Now, what you see here is that pressure and volume are being multiplied, just like in the individual laws. Now, we said that moles and volume, Avogadro's law, were being divided. And if you want to put them on the same side, you'll have to end up dividing n. And here you see Avogadro's law, for example. You don't have to write this down. It's just for you to see how the individual laws come together in this big gas law. So what this law does is it allows you to figure out one of these unknowns if you know the other three. So for example, you know pressure, volume, and moles, but don't know temperature. You can solve for what the temperature would be. If you know temperature, moles, and volume, you can solve for what the pressure would be. And that's the whole idea here. Now, it's important to see that R, gas constant R, has a number, 0.0821, pretty famous gas law constant. And its units are, there are four parts to the units. And the units are liters, atmospheres on top, moles, and Kelvin on the bottom. Now, the reason why the units are so strange is because constants usually tie together all the variables in the equation. So the constant has to have units of volume, here it is, liters, units of pressure, ATM, units of moles, that's what N stands for, and temperature, that's what K. So in other words, you see all four of these parameters in the units. And the reason they are liters, atmospheres over moles, Kelvin is because if you rearrange this whole equation to solve for R, and if you say, all right, R, this means I have to move the moles here, I have to move the temperature here, that's how you get PV over NT. Whoops, NT. And that's why the units match up. So a little more information. And this is important now. Whenever you're using this equation, you have to make sure your pressure is in atmospheres, your volume is in liters, and your temperature is in Kelvin. So if you're given another unit, you have to convert. If, for example, you're given Celsius, you have to convert to Kelvin. If you're given torr, you have to convert to atmospheres. If you're given milliliters, you have to convert to liters. And that's what we'll do as we go along here. Okay, so that's the idea. We're actually going to use this equation and solve problems with it. Simple as that. Why don't we try? There's really two of them that we're going to do together. Why not we go ahead with two of them? So the first one, example 7, says what pressure is exerted by 0.325 moles of hydrogen gas in a 4.08 liter container at 35 degrees Celsius. So we're asked for the pressure. Our equation, PV equals nRT, has to be rearranged to solve for pressure. So we have to get pressure to be by itself, essentially. Now, it sometimes helps to write out what we're given and then plug it into the equation. So pressure, we're given a pressure of, well, what is the pressure? We don't know. That's our unknown. That's what we'll be finding out. We're given a mole value, so moles would be 0.325. We're given, this one here is volume, so we're given volume of 4.08 liters, and maybe we should put an equals here to see that that's not a minus. And then we're given a temperature of 35 degrees Celsius, so our temperature is 35 degrees C. And now we're going to rearrange the equation to solve for pressure, which means pressure will be, you'll have to divide volume away from pressure, to the other side, because volume right now is being multiplied. To get rid of it, you have to do the opposite. So now we have volume on the bottom, we have nRT on top. Before we plug these values in, we have to make sure all the units are in their proper unit, essentially. And moles is good, volume is good, but temperature is not. We have to convert temperature into Kelvin. You remember how to convert? You would add 273. So the Kelvin temperature was actually going to be 273 plus 35, which should give you 308. So we're not going to use the 35, we're actually going to use this temperature right here. Alright, so go ahead and let's plug in the numbers. Moles is 0.325. R, it's going to get a little crowded. Let me see if I can extend it just a bit. Let's do it down here. Different color. So moles would be 0.325. The constant R is always the same. It's always 0.0821. Temperature in this case is 308. And volume is 4.08. Go ahead and plug this into your calculator and see what you get. Do 0.325, multiply by 0.0821, multiply by 308, divided by 4.08. You should get a final volume of 2.01. Now we have 3 sig figs, which is fine, so 2.01. Question is, what would the unit be? We're solving for pressure, so the unit would be atmospheres, because R is defined in ATM. Now I left the units out of these, but let me show you real quick that if I were to leave the units in, they would also cancel out. So in this case, this is moles. This one is actually liters atmospheres, moles Kelvin. This one's Kelvin, and this one's liters. What you'll see is that everything cancels out. The moles cancel out, the Kelvin cancels out, the liters cancel out, and notice it's a little tough to see, but you're left with ATM, exactly what we should be solving for. So this works out perfectly mathematically. Okay, the problem itself isn't that difficult. Let's try a different one, one that maybe looks a little tougher, but really it's the same idea. Example 8. How many grams of oxygen gas are there in a 2-liter bottle under STP conditions? This one sounds a bit tougher because it doesn't seem like we're given enough information. So first of all, we're asking to solve for grams. Now grams, remember, is connected to moles. You can go from grams to moles using the periodic table. That is how we go from grams to moles. Here is a picture of correct error. If you want the F block for your visual pleasure. So really what we're solving for is moles. Let's first solve for moles. That is the one we don't know. That is the one we're going to be solving for. Okay, we're told 2 liters. What is that? That is volume. We have 2.0 liters. And we're given STP conditions. Now remember, STP conditions are standard temperature and pressure. So we're actually given temperature. We're actually given pressure. And STP, the temperature is 0 degrees Celsius or 273 Kelvin. The pressure is 1.0 ATM exactly. So these are our STP conditions. And if you look previous in the notes, you'll find us defining these STP conditions. So what do we solve for? Let's go ahead and solve our equation for moles. Remember, our equation is PV equals nRT. In order to solve for moles, we have to divide by R and T, or we have to divide away R and T because they're being multiplied. So N equals PV over RT, which means our pressure is 1.0, our volume is 2.0, our value is the same, 0.0821, and our temperature is 273. Now, when you're dividing this, I would advise you to multiply the top, multiply the bottom, rewrite them, and then divide those two numbers. Because if you plug these numbers into the calculator, if you do 1.0 times 2.0 divided by this times this, you'll get the answer incorrectly. You have to divide by both of these. So 1 times 2 is 2.0 on top, 0.0821 on the bottom times 273 should give you 22.413. And so we have ourselves 2 divided by that for a total answer of 0.08923. Now remember, this is moles. However, we're asked for grams, so now we have to convert moles to grams. So one more step, and we begin with 0.08923 moles. This is oxygen gas, and oxygen gas, remember, is diatomic, so O2. 1 mole of oxygen on the bottom, and then grams would be 32 from the periodic table. If we divide this, or multiply this out, we should get ourselves a fine value of 2.86. We have 2 significant figures, so 2.9 will do it. So let's go ahead and put 2.9 grams, which is our final answer. So notice we've used the same equation to solve for a different parameter, and these hopefully are not too difficult. They do have a few tricks, or not tricks, but a few curveballs like the one you see here with grams. We may throw a few more curveballs, make you convert from milliliters to liters, from torr to atmosphere, something like that. But all of them essentially use this famous equation, the ideal gas law equation. So this completes for us Unit 11, Lesson 7.